Today, we want to find some more antiderivatives. We want to start combining some functions. We want to look at some variations on the base examples that we had yesterday. So yesterday, we learned integral of power functions. So x to the n, that was useful. We even had the integral of 1 over x is natural log of absolute value of x. We learned integrals of e to the x, sine of kx, e to the kx, sine of kx, cosine of kx, tangent of kx. Or actually not tangent, we learned integral of secant squared. Kx is tangent. And we learned the integral of secant tangent. We learned the integral of 1 over 1 plus x squared. And we learned the integral of 1 over the square root of 1 minus x squared. So we took a bunch of stuff that we already knew about derivatives and just flipped it around to become integrals that we now know. What we need to do now is look at some more techniques. Just like with derivatives, where we had product rule, quotient rule, and chain rule, we're going to take those facts about derivatives and then turn them around to become things that we know about integrals. I was going to start with an example that we had yesterday. So if you recall, we had the derivative of, I can't remember where I started, so I'm just going to pick one. We started with a derivative and then we turned it around. The derivative of sine of something is cosine of that thing times the derivative of that thing. So the derivative of sine of x cubed we're going to use the chain rule, so we're going to identify a function that's outside and a function that's inside. So if we think of what's going on here, the x cubed is the inside. And what we're taking the derivative of is the sine function. So sometimes we refer to this as the inside and the outside. So when we read this derivative, we take the derivative of the sine of something. In this case, the something is x cubed. So the derivative of sine of something is cosine of that thing. Take the derivative of the outside, leave the inside the same, and then multiply by the derivative of the inside. So then the chain rule says, multiply by the derivative of the inside. Take the derivative of y with respect to u, multiply by the derivative of u with respect to x. So cosine of x cubed is the derivative of y with respect to u, and then we multiply by the derivative of u with respect to x. If I switch the order of inside and outside functions, I'm going to be looking at a different function. Let's look at that one. Let's switch the order of sine and cube and find the derivative of sine cubed of x. In this case, when we write sine cubed, we mean take the sine of x and then cube the result. That's the opposite order that we had in the first example. In the first example, the order of operations would say, find x cubed, take the sine of the result. But in the second one, we flip those operations around. Take the sine of x and cube the result. So sine of x cubed, we're really looking to take the derivative of sine of x cubed. So that's what we mean when we say sine cubed x. This is just one of those strange ways we write things. We happen to write the powers of sine in this weird way. It's specifically so we don't have to write all these friggin' parentheses all the time. We got lazy and we're like, oh, hey, I got an idea. Let's take this cube and stick it next to the sine and just read this sine cubed x as the cube of the sine of x. Like I was there. I missed that day. So now we've switched the order of the operations. The inside is sine of x. And the outside function, the thing we're actually taking the derivative of, is an x cubed function. So I want to take the derivative of sine cubed x. We're taking the derivative of something to the third power. The derivative of something to the third power is going to be 3 times that thing to the second power times the derivative of that thing. In the first example, the derivative of sine of a thing is cosine of that thing times the derivative of the thing. In the second example, the derivative of something to the third power is 3 times something to the second power times the derivative of that something. That's where the chain rule comes in. We should note that we are always using the chain rule. The last step in the chain rule is that the derivative of x is equal to 1. So when we take the derivative of x to the third power, it's 3x squared times the derivative of x, which is 1, and that's how we know when to stop. You've always been using the chain rule. Wizard of Oz style moment there. Oh, you've always been using the chain rule. It's just that the last step in the chain rule is that the derivative of x is equal to 1. This isn't how we would write this particular expression. We would say sine of x squared, or the square of the sine of x as sine squared x. That's how we would normally write this. We would say 3 times sine squared x. Any questions? Just like it above, we wouldn't write the 3x squared at the end, mostly because we have 4 parentheses discipline. So the normal way to write this would be to write the 3x squared first. We like our polynomials to go first, and then we would write our trig functions. But the important part of this problem is reading what's going on. So we need to turn this reading around. We need to look at these derivatives that we found and come up with a system for going from this derivative back to the function that we started with. So we want to look at this derivative and go back to the function that we started with. We need to undo the chain rule. So we're going to look at an anti-chain rule. The anti-chain rule is called integration by substitution. Integration by substitution is a technique we'll employ when we look at a derivative and say, this derivative was found with the chain rule. So I'm going to use substitution to undo what happened. Here's what substitution looks like in general. We have the integral of a composition of functions. There's an outside function. There's an inside function. And then as a factor, we are also going to need to see the derivative of the inside. So I'm going to need the derivative of the inside to show up as a factor. Then we can integrate the integral will just be f of g of x. Notice that all I've done here is turn the statement about the chain rule into an integration statement. Normally, we would say the derivative of f of g of x is f prime of g of x times g prime of x. I just reversed that. What we're going to be looking for to do the substitution process is something that we can call the inside function and the derivative of the inside as a factor. And then the outside function is the one that actually gets integrated. Notice that if I wanted to integrate 3 sine squared x cosine x, we're actually integrating the 3 something squared. The integral of 3 something squared is something to the 3rd power. So it's the outside function that's the one that's actually getting integrated. The integral of 3 something squared is something to the 3rd power. In the previous problem, the thing that we integrated was cosine. The integral of cosine of something is sine of that thing. But what made it go was that we also had the derivative of the inside. Questions? So if we take this, we know that the derivative of sine cubed of x is 3 sine squared x cosine x. So if I wanted the integral of 3 sine squared x just from turning derivatives around, the integral of 3 sine of x squared, that's not right either. 3 times the square of the sine of x times the cosine of x. The integral of that is going to be sine cubed x plus c. Here's the color-coded version of what's going on. When I look at this, I see that the sine of x is sitting inside 3 times something squared. And I can use sine x as an inside function because I've got the cosine of x to be the derivative of the inside. So we think this cosine x showed up because of the chain rule. So what we're actually integrating is 3 things squared. And so the integral of 3 something squared is something cubed. Questions? We're going to do the same problem with just different insides. Let's suppose that we were going to integrate 3 times tangent of x. If I want to integrate this 3 tangent of x squared, what do I need to be see? What else do I need to see? That would be the derivative of the inside. What's the derivative of tangent? So when I read this function, I see 3 tangent squared, or 3 times the square of the tangent. And I also see the secant squared x. That's going to be the derivative of the inside. So this integral is going to be tangent cubed x. We're looking for something that we can identify as the inside function. Then we're also looking for the derivative of the inside as a factor. The only part that we don't need to see is a constant factor. Constant factors we can work around. So if I drop the 3 out of this, so let's suppose I wanted to integrate, instead of 3 tangent x squared, I just had tangent squared. So in this case, our inside function is tangent. The secant squared is sitting there to be the derivative of the inside to make substitution go. That's the clue that this came from the chain rule. And we're integrating not 3 something squared, but just something squared. And so instead of having the integral of 3 something squared is something cubed, I have the integral of just something squared, which is 1/3 of that thing to the 3rd power. So I'll integrate something squared and get 1/3 of that thing to the 3rd power. The secant squared was just there to be the derivative of the inside. In these first two examples, we're just integrating 3x squared and coming up with x cubed. In the second example, the base model that was going on here is the integral of x squared is a third x cubed. Questions? How's everybody okay? Yes. This 1/3 here? Because what we're integrating is something to the second power. We're working on if instead of having a tangent of, instead of x, we just had tangent. The integral of something squared is a 1/3 x cubed. We add 1 to the exponent, we get the 3, then we divide by the new exponents. That's our process for integrating. Add 1 to the exponents, divide by the new exponents. 1 over n plus 1 times x to the n plus 1. Any questions?
This is not the same as finding. Yesterday you said.
Right. So yesterday we looked at an example where we had the integral of sine of x cubed, but we didn't have the 3x squared or a multiple of 3x squared running around. So that we didn't have the derivative of the inside, and that makes it not substitution. So that's what we have to look for here. If I change this problem to have the integral of tangent squared x, now we're not doing a substitution problem anymore. I want to view this as tangent being the inside, but if I'm going to call tangent the inside, I need to have secant squared as a factor to be the derivative of the inside. So this one is missing the derivative of the inside. So this is not a substitution problem. If I want to say that the tangent is the inside function, I need secant squared to be the derivative of the inside to make substitution work. How's that, okay? No, you're not okay. This is new and weird. So all of you that was not in are incorrect. You are not okay with substitution yet. I'm just kidding. You might be okay. But if you're not okay with substitution, that is the correct answer. If you're like, oh, dude, what the F is going on here? That is the correct answer. You're supposed to be in the phase of, Leach, what is going on here? We've done, let's see, we did one yesterday, 2, 3, 4. But this counts as an example. Non-examples are still examples, so 5. We've done 5 examples. I don't think you should go try out for the Giants just because you hit the ball 5 times. You are not ready. You have not had enough practice. You do a few thousand more integrals, then you'll get good at it. The truth is, there's only one way to get good at integration. You have to become a teacher so that you can teach Calc 2 like 30 to 40 times over the span of a 20-year career. That's the only reason that I'm good at integration. The first time I taught Calc 2, I was acting like I knew what I was doing. I just had to kind of pretend. Just like project confidence, don't answer questions. That's kind of it. When the questions come in, say, oh, no, I'll deal with that tomorrow. So tomorrow will be the perfect time for this. And then I'll work that example into tomorrow's lecture, because the fact is, I didn't know what the answer was right on the spot. So when you see a teacher do that, but right now, you can give me integrals and I will integrate the shit out of everything because I'm really good at it. It's one of my more useless skills. I'm also really good at written tests. It's been a useless skill for like a long, long time. But I'm really good at integration. At the end of this semester, I'd take any one of you into an integration battle. But right now, no. You'd just be liabilities. Don't get into integration fights. That'd be like, oh, well, I just got through my first class in judo and I got my yellow belt. I'm gonna go get into a bar fight. No, you're not ready. Integration fights aren't a real thing. I tried to make them a real thing. And then there's restraining orders. You get bailed out. And the administration's like, oh, you can't teach here if you're going to get into fights. I'm just kidding. I've never been fired for fighting the administration. Those records are sealed, so I'm just kidding. Those aren't sealed. I was fired for something completely unrelated. I'm just kidding. I left of my own accord. No one had to threaten me. What are we talking about? Oh, yeah. We need to know what the method looks like. We need a way to practice what's going on here. We need a way to practice what's going on here. We need to break this down into steps so we can practice the steps. Once we practice the steps, we can stop doing the steps. The goal of being in a math class is to not do all the friggin' steps. The whole point of learning the math in the math class is so that you don't have to do it anymore. But you start off by breaking things down into steps, and you go slowly through the steps, because slow is smooth and smooth is fast. Let's think about what this method should look like. Let's start with one that we had seen before. Let's have the integral of I'm going to write it in the more clearly inside function way. We already know what the integral of this function is. When you're learning a method, start with something that you already know to see if it'll work, or to make sure that it's going to work. Don't just jump right into new stuff. We're still looking for the same things that we did before. I'm looking for something that I can call the inside function. The only function that's sitting inside anything else is sine of x. I also wrote it in green. That makes it super obvious. So we want to identify the inside function. I'm going to say the inside function is sine x. Once the inside function is sine x, I've got to identify what is it sitting inside? What's the outside function? And it's that square, that's the outside. Now, to make substitution go, if we're thinking that we want to do substitution on this problem, if the inside is going to be sine x, I'm going to need the derivative of the inside as a factor. If we want the inside to be sine x, we need the derivative of the inside as a factor. Whatever you think is the inside, you need to be able to identify the derivative of the inside as a factor. So we need the derivative of the inside as a factor. It can't just be written there, it has to be included as a factor, with the derivative of the inside as a factor. And so once I say that the inside is sine x, I need to look for the derivative of the inside. So before I even go looking for this cosine x, I'm thinking if I want to say the inside is sine x, then the derivative of the inside is cosine x. And so I look back at my integral and say, do I have a factor of cosine x to be the derivative of the inside? And here the answer is yes. So we look back and say, have I got this? Yes. So we're good to go. This is a substitution problem. We have cosine x as a factor, so it is substitution time. Notice there are three things that we had to identify. An inside, the derivative of the inside, and the outside. What has the inside been plugged into? Do we have the derivative of the inside as a factor? That is what makes substitution go. If we just have, say, 3 sine of x squared, no substitution. I would want to say that the derivative of the inside is sine x. That's our only candidate. When we identify the inside, just as a reading exercise, we should identify what the outside is. So the inside is sine x. The outside is going to be 3 times something squared. But to make this inside happen, I need the derivative of the inside. And so I think of the inside, derivative of the inside. I'll spell it, try to spell it right. I look back at my original integral and say, there's no factor of cosine. This is not a substitution problem. There's no factor of cosine x. This is not substitution. Doesn't mean the problem is over. It just means that it's not a substitution problem. Since substitution is our only option at this point, we are done. The problem's not done, but we're done. Any questions? This is what we need to formalize. What we're going to do is give the inside a name. Like we're going to call it W. And so the outside is going to be a W squared. And then the inside is going to be a DW. So tomorrow, we'll look in more detail at the method of integration by substitution. That's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.